Good morning, one and all. I am Udeshri, working as Assistant Professor in the Department of Mechanical Engineering in St. Peter's Engineering College. Today, we'll discuss about solid modeling technique, which is a part of Unit 2 in CAD/CAM. In the previous class, it means in the last video, we have discussed about surface modeling and wireframe techniques. Now, let us discuss about solid modeling technique. Solid modeling. Solid modeling technique, we also call it as a complete representation. The reason behind calling this solid modeling technique as a complete representation is, see, in case of wireframe model, you can just find the lines. So everything will be represented with the lines, and that model is more confusing because you cannot differentiate between the lines which are at the back and which are at the front. And at the same time, we cannot say whether the component is a hollow component or a solid component, and there is a lot of confusion if you go for the models which are very complicated, and at the same time wireframe model cannot be used for machining purpose. In the sense, you cannot generate any NC program or else the process sheet with the help of wireframe model. To overcome the limitations of wireframe model, we have come for surface modeling. In case of surface model, you will get a surface over the required frame, means required the wires, but the thing is, here also you cannot say whether it is a solid model or a surface model. It means whether the component is hollow inside or filled inside. But here, in case of solid model, you can differentiate between a hollow component and a filled component by taking a cross sectional view. Cross sectional view in the sense, if you have some component, you can cut it in the middle in the software, and you can see what are the things which are present inside. So that is about solid modeling. So this solid modeling can be easily drafted. It means once you produce the model, and if you open the drafted sheet, this component will get projected over the sheet in all the views, and dimensions will also get generated automatically. So the controlling of views and the controlling of dimensions is depending upon the person who is drafting. So based on your convenience, based on the things you want to see, you can make the drafting, and also you can make the dimensions. It means you can make it in two ways. The system will also generate, or else if you want to make, you can make a drafting of this. And at the same time, this solid modeling technique can also be used for making NC and NC programs, and also in generation of process sheets. So this is how solid modeling will help us to understand the design and also the manufacturing. It means both the design and manufacturing will become easy with the help of solid modeling. So now, in order to understand the solid modeling techniques, we have to know what is geometry and what is topology. So now let us discuss about what is geometry and what is topology. So now if you look at the first figure here, okay, and this one, consider these two. See, here you have same geometry and different topology. So now what is geometry and what is topology? Geometry will explain you about its length, means all the dimensions. It can be length or width or radius or height or whatever. It just represents the dimension. And topology will speak about the connectivity between the edges. So now here you see it is written as same geometry and different topology. Same geometry in the sense same dimensions. So here you see L1 and L2 are of same length. L2, so this L1 and this L1 are of same length. This L2 and this L2 are of same length, and this length and this length L3 and L3 are same. Okay, here radius is same, and here also the radius is same. Here also you have the same center, and here also you have the same center. So here geometry is same. It means all the dimensions are same. But here you have two different figures. These two figures are not same. In the sense, you have a different topology. It means the connectivity between the edges is different, but the dimensions of that particular figures are same. So that's why we are calling these two things as same geometry and different topology. But here if you see these two figures, we say different geometry and same topology. So here see L1, L2, L3, L1, L2, L3, radius and radius. See, here also you are representing L1, L2, L3, L1, L2, L3, R and R. So here there is some angle. Okay, it means there is some difference in the geometry, but the thing is here the connectivity between the edges is same. See, L1 is connected to L2, L2 is connected to L3, and L1 and L3 are connected to the radius. So here you have the different geometry but same topology. So here the point which we need to remember is geometry will speak about its dimensions like length, width, height, radius, etc. And topology will speak about the connectivity between the edges. Okay, so these things we have to remember in order to understand the concepts which are coming next. Okay, so primitives. We have already learned about primitives in the last unit, but here also in order to understand the coming up techniques, geometric techniques, we have to know what is a primitive. So I am revising it once again. But here we will understand about primitives in depth. It means more than what we have learned in the last class. So here the first one is cube. Okay. Now in order to define a cube, see primitives are some geometric techniques or geometric models which are used to make some solid models. So we take these things are basic shapes in order to get the required geometry. So the first one is cube. So in order to define the cube, what we do is if x naught, y naught and z naught is the origin and x, y, z are the axis, it means our coordinates, then we represent this cube with its length, width and height. Okay, see for example, if you are taking origin here at this point, so uh, the length and this width and this height. So these things will represent a cube. Similarly, for a rectangular prism or else a rectangular box, whatever. So here also, if you are taking x naught, y naught and z naught as a origin and xl, yl and zl are its coordinates, then we represent this uh, rectangular box or a rectangular prism with x with its length, width and height. Okay. So this is about prism, and next one is a triangular prism, or we also call it as a wedge. So here in order to represent a wedge, we take origin at this point and we represent the wedge with its length and height. Similarly, this we call it as a sphere. We represent, if you can take origin anywhere, so if x naught, y naught and z naught is an origin, and if you have the origin of this sphere at some point called xc, yc and zc, then we represent this sphere with the help of the radius r. Okay. Similarly, here is a cone. Cone is represented with its radius or diameter and the height. And if it is a truncated cone, truncated in the sense the cone which is cut at the top. If you have a truncated cone, then we have to represent two radiuses. It means radius at the bottom, radius at the top and also the height. Next one is torus. So the axis of the torus will be in the middle. So in order to represent the geometry of this torus, we define two things. First thing is, see, generally this torus is formed by rotating a circle around some axis. It means if you have some axis like this and if you have some radius or a circle like this, now if you rotate this circle around this axis, then you get a torus. So here we will represent two things. First thing is the distance of this circle from the origin or from the axis, and also the distance of this circle uh, center from this circle center. It means we have to define distance between two centers and distance between this and the radius of this torus and radius of this circle. So these things we define. Next one is a cylinder. In order to represent a cylinder, we define the radius of a cylinder and also the height of the cylinder. So this is how we represent the primitives. It means these standard shapes will be already available in the software. We have to just give the dimension of the thing which you want to import into your software. So this is about different types of primitives. And next one is Boolean operations. Boolean operation is where we get a new model by applying some, by adding or intersecting or subtracting some model from the existing model in order to get the required model. To understand this better, let us take this example. See, for example, if this is a square and this is circle, consider this square as A and circle as B. Okay, union is A plus B or A union B. Okay, intersection is C, the whatever the intersection points which you have between A and B. Okay, here you have subtraction. See, this is B and this is A, and here we are subtracting, means here it is B minus A. It means we are subtracting A from B. This is addition. It means adding of two. See, union and addition both are same. Okay. So that is, so this is about Boolean operation. Now in order to understand the next concept in the same video, we should know what is Boolean operation and what are primitives. Okay, now let us see about geometric modeling techniques. We have different geometric model techniques. First one is boundary representation. Next one is a constructive solid geometry. Next is sweep representation. This sweep representation is divided into two types, that is linear sweep and non-linear sweep. And linear sweep is also two types, like extrusion sweep and rotational sweep. And next one is a hybrid sweep and invalid sweep. Next one is space parting representation. We have two representations here, spatial occupancy and cell decomposition. So now let us look at all these things in this video. First one is a boundary representation. We also call this boundary representation as B representation. So here we use both geometry and topology to represent the component. So how we define the geometry and how we define its topology. See here you can see node 1, node 2, so on. So these are the nodes. So these are the nodes. So here you have nodes. So all these points are the nodes. So the nodes, because of the nodes, you'll get the length, width and height. So here you are getting the geometry. At the same time, see you have faces, edges and vertices. So we are joining these things. Okay. So here you have topology. So boundary representation is where you use your geometry and topology and join the surfaces. It means make a boundary in order to get some solid model. So that is about boundary representation. Next one is a constructive solid geometry. See, as I told you, here we are using different primitives and also we are performing some Boolean operations. So here what we do is, see, this is the final part which you want. Okay, in order to get this final part, what the things we have to perform. So that is this constructive solid geometry representation or C representation. So what we have to perform is, see, first we have to take this block and then join with this block. So joining is called union. So here you see this is the part 1 and this is the part 2 and this is the union. It means you are joining and getting this L-shaped block. Okay, and from this L-shaped block, in order to get this circle, you have to subtract a cylinder. Okay, so that's why whatever the part you have got, and from this you are separating this part 3. It means this is a Boolean operation, subtraction, minus. So you are subtracting this part and getting the final part. It means first you are making an L-shaped part and then subtracting a cylindrical part. So this is a C representation, that is constructive solid geometry representation. Next one is the linear sweep. Linear sweep is of two types. First one is a translational or extrusion. Next one is rotational. So in case of translational sweep, what we do is we make one required figure and then we extrude it in the required direction. See, if this is the figure, now we are extruding it in defined direction. So this is called a linear sweep or a transitional sweep. Next one is a rotational sweep. See, this is a rotational sweep. So here we have an axis and you have a required 2D sketch of the model. So what we do is we make only just this line and we just rotate it along the required axis in order to get the required figure. Yeah, see, if this is a required sketch and if you are rotating, you will get the 2D model, so 3D model of required sketch. So this is about rotational sweep. So this is the translational sweep and this is the rotational sweep. So these two will come under linear sweep. Next one is a non-linear sweep. In case of non-linear sweep, we will be having a curve and the required figure, the 2D sketch which you are making, will get sweep along the given curve. So this is a non-linear sweep. Next one is a hybrid sweep. Hybrid sweep is a combination of linear and non-linear shape. Okay, so here you can make this non-linear shapes in different ways. So here, see for example, if you have this L-shaped block, okay, you can extrude. If you are extruding in different directions, then it is also a hybrid sweep. Or else if you are making this L shape and subtracting this from this, means you have this block, first block, and if you are separating it from second block, then also it is an hybrid sweep. It means if you are combining both linear and non-linear sweeps. Or else you see, if you are having straight lines, even if you have a curve here, and after that you are making some Boolean operation, it means you are combining both linear and non-linear sweep. In that case also we call it as hybrid sweep. So wherever you have combination of different types of sweeps, then we call it as hybrid sweep. Next one is an invalid sweep. Though it is invalid, sometimes we use this. What generally we say is, when we have not performed sweeping operation correctly, then we say this as invalid sweep. But the thing is, in nowadays, while making some components, sometimes we are performing this type of sweeps also. It means, see for example, if you have some component like this which is very straight, and if you are taking the path at some angle, and if you are performing some operation and subtracting the required curve from this, then we'll get this type of sweeps. So here that we call it as an hybrid sweep. But when we are getting a errored figure, in that case we call it as invalid sweep. Next one is spatial occupancy enumeration. In the sense, see, you have a component divided into small blocks. Okay, so what we do is, we have a big component, and that component will be divided into small parts. So the main purpose of dividing this component into small blocks is to perform some analysis in the sense, before making the component practically, we make a 3D model and we divide it into small squares and perform a stress analysis, or any analysis, stress, strain, total decomposition, any analysis which you perform. So here, as we are dividing the component into very small blocks, we'll get an accurate result, in the sense where you are getting more stress, where it is getting deformed to the larger extent. So all these things can be understand. So spatial occupancy is, you are dividing the component into small cells, and this is more suitable for performing the analysis. That is about spatial occupancy enumeration. Next one is cell decomposition. Cell decomposition is, see here you have different primitives. We'll just join the primitives in order to get the required component. But the one thing which we have to remember here is, no no primitive will overlap with another primitive. So there is something in the middle called as glue. So it just joins both the primitives, but it does not means, it joins both the primitives, but there will be no intersection between both the primitives. So this is about cell decomposition. But here we use different components, means different primitives. But what we say is, spatial occupancy is more suitable for performing the analysis when compared to cell decomposition. So both the things, in case of spatial occupancy enumeration and also in case of cell decomposition, there will be no intersection between any of the primitives. So the smallest components here, this small box, are called as voxel, VOXEL. So these are the smallest cells which are used for performing the analysis. These small cells, means any component can be divided into these small cells. The smallest part of any component is called as voxel. So that is about spatial occupancy and cell decomposition. So here, see, if you look at this figure, you have some triangular block, and also you have some rectangular box, and you have two square blocks. So these are the primitives. So with the help of these primitives, we are making some component. This is called as cell decomposition. So this is about surface modeling technique. Thank you.